The formal part of the introduction was done by email. And if you're not on that list and would like to join, be happy to add you to the list. I'll put it in the chat here in a little bit. Our normal mode of operation is to ask people to mute themselves, but encourage them to interrupt with points of clarification along the way. And then at the end, we'll have probably about a half an hour for questions and answers and a discussion period. So with that, I'll turn things over to Akari. Thank you very much for putting this together and for agreeing to give a talk in this mode that, okay, it isn't perfect, but it has some advantages. So thanks very much.
Yeah, thanks for organizing, Chris, and thanks for the invite. And yes, like Chris said, I thought I'd use this opportunity to talk a bit about heterogeneity of faults, or heterogeneity in faulting from a sort of field perspective. Looking at a few different examples. I've put a bunch of names underneath here because, as with every sort of talk you give from pulling together a bunch of projects, a lot of people have been involved with work I've done in the last 1 or 2 decades. But I'll also just refer to people as I go. There we go. So as a quick outline, since it's sort of a slightly longer talk, I thought I'd start with a little bit about fault zone structure and fault rocks and fault mechanisms. It might be familiar to a lot of you, but just to kind of get us on, make sure we're on the same page in terms of nomenclature. I then want to talk a bit about low stress examples of fault heterogeneity, specifically about some features from subduction zone settings, and then switch gears and talk a bit about high stress examples. So, earthquakes where you might not expect them, so relatively dry crust, dry lower crust, so relatively high temperatures. And then a bit of a discussion, which is more maybe discussion points for later than pretending I have any solutions. Now, in terms of talking about linking fault rocks with mechanisms, that's not something I'm starting from scratch. I was lucky enough to do a PhD with Rick Simpson, and he had most of the ideas I have a long time before I did. But this general theme that we have a brittle upper crust dominated by cataclastic deformation, a ductile lower crust, a viscous lower crust, dominated by the distributed flow, and then some transition zone in between. That's been around for a long time, and could be related also to frictional stability, with the seismogenic zones frictionally unstable, a deeper zone that's more stable, and that somewhat relates to a transition from where frictional sliding is easy and dominates at shallow depths, and then at deeper depths, viscous deformation is easier because temperatures are high and pressures are high. So that causes this switch from whether frictional sliding is easier or whether viscous creep is easier. And you see that in the geology broadly as a rule of thumb, as a change from discrete faults at shallower depths to distributed myelonitic shear zones at deeper depth. But there's a lot of exceptions to that. We have earthquakes at high temperatures in the lower crust. We have distributed shearing flow at shallow depths and low temperatures. So while this is a good rule of thumb, it's not a end all and be all of how faults work. But let's start with some end members. An end member view on what we see in the shallow crust. When the brittle crust is principal slip zones. Here is an example from San Gabriel fault, so a subsidiary of the San Andreas. Very localized fault surface. If you go closer, it's a few centimeters thick, well studied, seen to be a place where slip is localized onto a single fault plane with basically embedded in an elastic medium. Kind of how we often think of faults. And in that sort of paradigm of very localized slip surfaces, you also have examples of pseudotachylite, so frictional melt along slip surfaces. This one's from Moonlight Fault, part of the Alpine Fault system in New Zealand. And you see a very local slip surface, vitrified melt that comes along that fault surface, but also has been able to infiltrate into surrounding fractures. And you see examples where that's not only localized to a single surface, but might infiltrate wider zones of fractures, but probably emanates from one or two surfaces within the system. But anyway, point is, we do have examples where faults are planar, and slip localizes in earthquakes on those planar faults. We have examples that are a bit more complicated, where there's more than one slip surface. This is the Husavik transform fault on Northern Iceland, where we have multiple slip surfaces embedded in a damage zone. So by damage zone, I mean a volume of damage host rock that exists around one or more principal slip zones. Commonly, that's defined by an increase in fracture intensity relative to a background. And typically those fractures are dominantly tensile, so do not really participate in accommodating shear displacement. And there's several examples of faults like this. I mean, Dan Faulkner and Ernie Retter has made Carbonera's fault in Spain famous. And in some places, like on the right, you have one of these principal slip surfaces next to a damage zone, but that damage zone is healed. So you have two end members of damage zones. They might stay open and stay as open fractures that are relatively weak, or they might heal with, in this case, a precipitate, so that they're basically back to wall rock strength. Obviously also with effects on permeability. So to just think a little bit more about what a fault zone like this looks like, you have a fault core that takes up the most of the shear displacement, and it's surrounded by fractures that decay in intensity away from the fault. And it's not uncommon that you also have a chemical alteration zone related to that fault zone damage. So if we look at an example of a damage zone, here are some images from the Zomba fault in Malawi, which basically has this kind of geometry. It's a normal fault. It has a damage zone on either side, we think, although the hanging wall is not well preserved, so this is all looking at the footwall. But if we start nearest the fault on the left, you see damaged rock, lots of browns and yellows related to clays. If we just highlight the fractures in red, the fracture system is intense. It does not have much of a preferred orientation, cross-polarized light. So this is all in thin sections, the 500 micron scale bar. You see the clay is a bit better. So a lot of alteration, a lot of fractures, variable orientation. You go a bit further away, you have less fractures, but still a lot, but more of a preferred orientation that is more or less fault parallel. You go further away, less fractures, and further away again, and you're down to a background fracture intensity, which has a preferred orientation, but it's not related to the fault. So the kind of two features, lots of fractures near the fault, less away, and that's also related to alteration. So that alteration might have an effect. I said earlier that my definition of damage zone here is that it doesn't really participate in deformation. Deformation happens localized on principal slip zones, but that isn't always the case. So Bob Holdsworth group, for example, has pointed this out many times based on the Outer Hebrides, that there the alterations has reached a point where you've essentially had an alteration-driven frictional viscous transition where you see blocks of intact rock, but then the surroundings are altered to clays, chloritic mostly in this example, that take up deformation by distributed shearing flow. And you can see the same in this example from Nishizanogi metamorphic rocks in Japan, subduction setting, but here you have something that used to be a basalt. It's deformed, altered to mostly chlorite, and it takes up a large amount of distributed shear in the footwall of this dominant thrust here, which juxtaposes it against a pelitic sediment. But again, you then have, rather than a principal slip zone in a fracture damage zone with little shear strain, you have localized slip surface still, but now in a broad zone of shear. So Cristiano in the audience there, he summarized this very nicely with this effect that you can start off with a bially friction rock, you deform it, you infiltrate fluids, and you change its behavior to something much weaker, but also you go from localized sliding on one or more surfaces to a behavior that's more dominated by distributed flow. And you can illustrate that with an example. This is from Sophie Cox's work on a transform fault on Cyprus. But there you start off with basaltic dikes, sheet of dike complex. You develop faults along the dike margins, and then you start fracturing the dikes, which allows fluid infiltration into the dikes, which then increases the proportion of clay-rich matrix. And then you keep deforming that, you infiltrate more fluids, make more clay-rich matrix, and in the end, you're essentially left with a broad zone of sheared clays, whereas you started with intact solid dikes. And we did some experiments on those. And
okay, sorry, can I ask you a clarification here?
yeah.
So can you better clarify what do you mean when you say that the damage zone does not participate in the processes occurring in the core? Is this depending on the seismogenic behavior of the faults or not? So because for us, when you do dynamic calculation and dynamic rupture propagation, actually the damage zone is an energy sink. It does affect what is happening in the core. So
yes,
I better understand what do you mean when you say not coupled.
Okay, I don't mean it does not have an effect. I mean, so that was poorly worded. I mean it does not accommodate shear strain. So the dominant, or not much shear strain. So the shear strain or the displacement dominantly occurs in the fault core, but that doesn't stop the surroundings being an energy sink. But if you look at it structurally, you see the displacement localized across the core. And within the damage zone, displacement is very small in comparison to the displacement across the core. Does that make sense?
Yeah, okay, thanks. But
Yeah.
this is just a comment for the discussion behind, because this is important, because there are many colleagues of mine who are speaking about the damage zone, and they put aftershocks, even magnitude 4 aftershocks in the damage zone. Therefore, I believe that there is a quite different, some confusion between terminology of what is a geological damage zone, as you presented, and a fracture at the medium, when you can have different earthquakes in a complex fractured systems, which is not a damage zone. So this is my point. Thank you for the clarification.
Can I make a comment about that? It's Chris Schultz. Perrin et al., this was a couple of years ago, wrote a paper about that subject in which we described two damage zones, and a dilatant damage zone, which is mainly mode 1 cracks, which is what Aki has been talking about, and a shear damage zone, which extends out much further. And that's where you have the distributed aftershocks occurring. So you have a broader damage zone in which there's shears, mostly parallel to the main fault, that extend out maybe 3 or 4 kilometers, whereas this dilatant damage zone is maybe only extends out 100 meters or so. And so there's 2 damage zones you can discuss. Thanks.
Good point, and I'm going to get to that in a second. Thank you. So in this sense, thinking back to Cristiano's model, and with the discussion we just had, you're starting with something that is a relatively intact rock, close to bially friction, you deform it by dominantly dilatant damage, and slip along, a distributed set of principal slip zones, or localized fault surfaces that in the transform example we have here, there happens to be well-oriented dike margins that serve that purpose. And then the dilatant deformation in between allows fluid infiltration and then creating this broader zone of shear. Just in terms of how properties evolve when that happens, when a fault develops in that particular way. So this was in Matikari's lab in Bremen. But we basically we start with something that's a class proportion of 100%, so an intact dolerite that is velocity weakening, Bailey friction. You deform it a little. You take a sample that has been deformed a little bit, altered a little bit, 70% dolerite left, not much has changed. And you then get to a point where more than half of it has deformed or has been altered to clays. You then have a switch from being velocity weakening to velocity strengthening, from being Bailey friction to being weaker than that. And then again, if you go even more evolved example, more clays, more stable, substantially weaker. And if you when we looked at the samples from that post-mortem, the dolerite samples basically have principal slip zone in a damage zone, dilatant damage zone. The more gouge-rich rocks have a broader deformation zone, broader shear zone, and less of the dilatant damage. Now, another point to make is you can make fault zones like the weaker, more distributed shear zones without the alteration stage. So you don't have to start with a Bailey friction rock, break it up, alter it to turn it into something that can deform by broad distributed shear at low temperatures. You can take something like a subduction thrust, where you have an incoming sediment sequence that is already clay rich. And you might end up with something like this shear zone from Shimanto, from the Shimanto melange in Japan, where you have dominant clay-rich sediments with clasts of sandstone layers embedded in it. And Christy Rowe and others had a very good review on the sort of hierarchy of shear zones that develop in that setting, where you have a melange that's hundreds of meters or even kilometers thick. And within that, you have discrete faults of some spacing that depends on largely the lithology and fluid distribution and several other things. And those might organize into fault zones that are tens to hundreds of meters of thick within this wider melange. So you have a range from very discrete faults to broader zones of shear, and not so much maybe the dilatant shear zone that you expect if you have just one or more principal slip zones in a more homogeneous medium. So what I've been trying to get at in this introduction is just that we have a range of styles of faulting, from planar faults in a more or less rigid medium that may be surrounded by dilatant damage zones, to wider zones that are more zones of broad shear, where you might still have principal slip zones, but you also have a broader zone that accommodates shear. And you can make that by starting from something like these zones on the left and altering them, or you can make that from just having a starting material that already has a broad, weak, relative to the surroundings, zone that can deform by distributed shear at low temperatures. So to try to summarize that sort of range of faults in a figure, there's the top two examples here, which is really just stolen from Faulkner's 2010 review, where you have a single slip zone in a damage zone or multiple principal slip zones in a damage zone, here again meaning dilatant damage zone. Although here you could have a wide zone with multiple principal slip surfaces where one might host an earthquake and another one might host an aftershock. But then you also have, in scenarios where you're able to distribute the shear, so as a function of basically how much slip is on localized surfaces and how much is distributed through a broader shear zone, you might have a shear zone that takes up most of the displacement as finite strain within a wide ductile shear zone. Ductile used intentionally as an ambiguous term of what mechanism is accommodating that. And within that, you may or may not have principal slip zones. If in this comparison of principal slip zones in dilatant, dominantly dilatant damage zones, if the fault is weak relative to the wall rock, as soon as you've got one, you don't really need to make more. Whereas if the faults are effectively healed, or for some other reason there's a similar strength to the wall rock, you might develop this larger number of principal slip surfaces. In this example, where you have some weaker ductile material, if that is a lot weaker than the host rock, then you have large strength gradients between the flowing material and the wall rock, and you might end up that way amplifying stress locally and then create, say, through-going principal slip surfaces or local fractures within the wall rock. Whereas if the stress gradient or strength gradient, sorry, is small, you're more likely to have something that develops more homogeneously and maybe less the reason to develop multiple principal slip surfaces. Again, that's me somewhat speculating, but there seems to be an opposite relation between strength gradient and number of slip surfaces that develop, whether you have a wide ductile shear zone or a more coherent dilatant damage zone. Now, in any of those cases, there is a development of heterogeneity at some scale. You might have, if you have a single slip surface, you have asperities at the fault scale. So asperities here are used as just sticking points on a frictional surface at the microscale. Then if we step up to, say, an outcrop scale, you have a much more complicated system with potentially many slip surfaces that have their own microscopic asperities, but they're also interacting with each other and different host rocks. And then we often attempt at stepping up another scale and saying, well, there are some areas that seem to be more, or releasing more moment, which is a different form of asperity than what you used here. And there might also be sticking points in what is nominally creeping, creating small earthquakes, what's also often referred to as asperities without necessarily being the same thing as here. So what are these different heterogeneities in different settings? Is something to wonder about and something to think about. So when I'm talking now about effects of fault zone heterogeneity, I really mean that, whatever the reason, there will be some fault zone strength heterogeneity leading to some spatial variations in the response to remote stress. So, some air fault segments might be able to accommodate strain aseismically at a given strain rate. So say at plate rate, you might have areas that are able to slide at that at that applied strain rate, and therefore do not accumulate elastic stress, and therefore, or elastic strain, and therefore stress levels are low. While you might have other points on a fault where the fault cannot accommodate the given strain rate at aseismically, and therefore stores up elastic strain over time, and therefore increases in stress over time. And then that variation itself will generate more stress heterogeneity over time. So one way of thinking about polyphase shear zones, now going to the examples in green on my previous diagram, where we have some wider zone of shear rather than principal slip zones in a dilatant damage zone. and say most of that is able to flow at some rate, and then there are lenses that cannot, or at least deform much slower than the flow of the surrounding rock. Then you have variations in strain rate across that shear zone, where some areas are strain rate is high, some areas strain rate is low. So high here, low here. And inevitably, there is then going to be a strain rate gradient at the edge, and you have effects on the bulk strength. So obviously, this is a bit stronger than having just the flowing matrix because of the clasts increasing the strain rate that has to be taken up by the weak material. But equally, it is weaker than if you had just the strong material, because a lot of shear can be distributed through the weaker component. So thinking about this in terms of bulk strength, stealing a diagram from Mark Handy back in 1990, if we plot composite strength over the strength of the strongest face in a two-face block, at very small amount of weak material, so phi W is weak rock proportion, you obviously have the strength is dominated by the strong face. Then if the viscosity ratio or the strength ratio between the materials is very small, then adding the weak rock doesn't do very much. Whereas if the strength difference is large, so a factor of 100, then you add, it seems to be about 20 to 30% of the weak material, makes it interconnected, and then that controls strength. So you kind of end up with three sort of end member behaviors of having a load-bearing framework. If you basically have the strong rock, you've got pockets of weak rock, it's not interconnected, strong rock dominates. You have relatively similar strengths than if it's a viscous system. You have you get some boudins of the stronger face in the weaker face. They act as a composite, and their strength is sort of a rough average. Whereas if you have a dominant matrix flow, then basically you're seeing a bulk strength that's close to or even equal to the strength of the matrix. So that's the bulk effects. And you see those in other natural examples as well. You see at the scale, this is on Anglesey in North Wales. You see in some places strengths are relatively equal. You have strung out layers of limestone here in a scaly fabric or mudstone. But if you look closer, what you see is, okay, the bulk strength is low and the bulk strength is a flow. But if you look at the components in detail, you have the blocks are fracturing and the matrix is flowing. So you have this competition between the brittle deformation of blocks and presumably aseismic flow of the surrounding material. So the surrounding material is generally controlling bulk strength, but it doesn't stop failure occurring in the blocks. Basically as an effect of this strain rate gradient between the surrounding material that can flow and the blocks themselves that can't keep up, but still need to deform to retain straining compatibility with the surrounding. And you see that at a range of scales. If you zoom in, this is a different setting in, or different subduction melange. This is Crystal's Beach in New Zealand, but you see a similar effect here of dashed red lines being faults, little faults in the matrix. So rather than the matrix just deforming by a viscous flow, it's a combination of viscous flow and then localized slip along basically clay-coated surfaces. And those are linked by tensile fractures in the surroundings, where again, you have some dilatancy related to the overall deformation of the zone. And then blocks themselves deforming either by slower viscous flow or by local fracturing. So the point I'm getting at is twofold. One is if you have a broad zone deforming, you can do that by viscous flow. You can do it by networks of meshes of shear and extensional fractures, or you can do it by a combination of those two things, so that the competition between different strengths don't just set what the bulk strength is, but also what the bulk mechanism is, but not necessarily without excluding other mechanisms. So you would have, in this case, you have frictional sliding on clay rich surfaces. That could be velocity weakening or strengthening depending on conditions. You have a lot of dilatancy related to tensile cracks, and you have a lot of local or very small scale diffusion driving then overall flow of the matrix. So to zoom in on that, thinking about what happens in addition to the fracturing in these melanges, you have, if you zoom in on the matrix, what you generally see is evidence for that quartz clasts here in white are basically surrounded by black cleavage planes, which are remnant clays and oxides from dissolution of quartz. So you then develop this cleavage system, stands out a bit more in an EDS, in a chemistry map, EDS map, where the reds are clays and the blue is silica. So you see that basically these cleavage surfaces are made up of clays. So that is an example of how pressure solution assisted creep or dissolution precipitation creep can accommodate some of the deformation at seismogenic temperatures if you have small enough grain size, low enough strain rates, so that where you would potentially just have quartz friction or phyllosilicate friction, you can also, if you have a wide enough tabular zone at some depth and temperature, say in this particular example and the assumptions we made here using Den Hartog-Inspire's formulation for the micromechanics, in a subduction zone thermal gradient, if you have a 100-meter wide shear zone, you might change from frictional sliding to dominant frictional viscous creep by coupled dissolution precipitation creep and frictional sliding at about 15K if you have a 100-meter wide zone, at about 25K if you have a 1-meter wide zone, shallower if it's even thicker. So idea is, well, you have a very weak mechanism available if you have a fine-grained, wet tabular fault zone available. But it does seem like there is always then, or often, then a competition between flow with pressure solution and with this coupled pressure solution and frictional sliding, and just localized sliding and fracturing. For a couple of reasons. One is that the cleavage that you make is enriched in clays, so it's weak, so it's easier to slide. And then also if the distributed sliding creates extension, that creates dilation, which then locally drops fluid pressure and increases strength, but then also drops permeability, drops solubility, so that you seal those fractures with quartz. So you end up with this interplay between fracture and dilatancy and pressure solution assisted flow and compaction. And also of strain rates, where if you can accommodate plate boundary strain rates with just pressure solution, then you shouldn't need anything else than creep in that fault zone. But if you can't quite, then you might have layers where you are accumulating elastic strain locally, and sometimes have to have earthquakes to catch up, as well as the heterogeneity internally. So we looked at this concept quite a long time ago now, with the idea of, well, where we named it dilational hydroshear, where the idea was that, okay, if you're going to have more space across foliation failure, that requires Bailey friction, that requires stresses we probably don't have, because pressure solution occurs at much lower differential stress than that. But if we think of our cleavage planes, they might have an elongfoliation failure criteria that only requires a frictional coefficient of something like 0.3. And that could happen, that could be activated with a Mohr circle out here. But we generally see evidence for that. If you have an example here of one of these shear surfaces, there's generally an optical continuity between the shear surface and tensile fractures, implying that the slip and the tensile opening happen at the same time, in which case we also need to overcome some tensile strength across defoliation, which implies failure condition more like this, which means normal stress is near zero, shear stress is very low, and we require a very high fluid pressure, at least exceeding the least stress in the system. And just since Chris is organizing, and I know Chris usually has a K sub C, in this reference, in this system, that basically requires normal stress approaching zero, so K sub C approaching zero, meaning these are inherently quite stable features. But they do form increments. So if we look at these slip surfaces in detail, we see little slip increments. Top one, crystal speech complex, bottom one, Shimanto complex. Yes. Schematically, we have slip on multiple little surfaces. They are linked by dilatant fractures. Those have slip increments on the order of a few microns, tens of microns. So if we apply that and say, well, these slip surfaces have length scales of tensometers max, they have slip of tens of micron. If we assume a shear modulus of a few tens of gigapascal, then that gives us a stress drop in the hundreds of kilopascal max. So very, very small stress drops, which has been in a few places suggested to be related to tremor. So basically that you have slow slip might be something distributed over the whole shear zone or on many one or more frictional slip surfaces, but then these little increments might be related to the tremor that happens at the same time. If we look at conditions for that at crystal speech complex, Makimina melange in Japan, and the Apennine subduction channel in Italy, all those conditions, this was an attempt by Jamie Kirkpatrick and others to plot all tremor conditions on a PT diagram, which showed that there wasn't much relation. But if we look at these specific locations where we see these dilational hydroshears, then they all set either at Lawson night out conditions or pre-night out conditions. So a place where fluid pressure is locally elevated by local production of fluids. So what I'm getting at with these is, okay, they are small, very low stress features triggered by high fluid pressures on very weak planes. And they seem to need just that. They seem to need, they're within a system that is deforming by distributed shear at very low stress conditions anyway. And the reason, or the simplest way of triggering them is not to have some sort of elevated stress concentration, but rather to have a local decrease in stress or a decrease in effective stress that makes frictional sliding easier locally where these features initiate. To think of that in a different example of the same thing, this is from Harry Lee's thesis work on Clarendon Island on Anglesey, where we can talk about complexity of Anglesey for a long time, but the thing to highlight here is you have basalt in green, oceanic sediments in blue and orange. So we have repeated sediments, or basically a repeated ocean floor sequence of basalt with sediments on top, fault, basalt with sediments on top, fault, basalt with sediments on top, so forth. So if we look at a fault like that, what we see it localizing into, in this case, we have basalt on the right. That's relatively intact or low strain. We have low strain carbonates, then very high strain chloritic melange and eolitic melange, and then relatively low strain sandstones. And if we look at that margin in detail, basically the same idea as I just said. We have strain localizing into these more clay-rich, lower friction rocks near this boundary. If you look at it in thin section, it has localized carbonate veins that are then subsequently sheared, which gave us an opportunity to try and get at what the stress level was. So if we do that, and look at the recrystallized grain size of the carbonate, so the blue in this plot, the red are not recrystallized, then we end up with a stress level of 80 megapascal plus minus quite a lot. But the allowed range of stress is 30 to 250. But with a average comes out at about 80, 90 megapascal. This is at temperature of about 270 degrees, depth not well constrained. But if we take that, and the point I want to make here is if you take that condition and look at the rocks that the strain localizes into here, you have distributed shear in a chloritic melange, basically governed by friction of chlorite in a stress against fluid pressure plot. So whatever the fluid pressure, so whatever the effective stress, the shear stress is about is, well, the shear stress decreases with more higher fluid pressure, but friction is the dominant mechanism. In the eolitic melange, there is more quartz with relatively low solubility, so frictional viscous flow with pressure solution becomes important at relatively high fluid pressures where friction is more difficult, and then you get above some fluid pressure where friction becomes easy. So the combined effect of those two zones is that at low fluid pressure, frictional viscous flow dominates, but then as fluid pressure increases, we have a switch to frictional sliding. And you can think in a similar way about how velocity affects how the shear zone behaves. If you plot shear stress against velocity, colored for fluid pressure, then basically as the velocity increases and shear stress increases, to get reasonable stresses, so around the stresses we determined, fluid pressure needs to be high, but not super high. At the same time, you see a change with velocity that the faster we go, the more slip is in the chloritic melange, which is frictionally weaker, versus the eolitic melange, which deforms more easily by pressure solution. So in this place, and the structures kind of look like that too. You have lots of frictional surfaces in the chlorite and distributed shear in the eolitic melange. You have pressure solution accommodating the formation at lower rates when stresses are, well, when fluid pressures are relatively high, so when stresses are a bit higher. And then if you locally increase fluid pressure, decrease effective stress, you have a switch-in mechanism, switch in which part of the melange takes up the deformation, and a potential change in velocity. I'm going to skip across my serpentine story because I'm running a bit low on time, and I do want to give another example. Coming back to that, where I'm getting at here is that if you have very low stress shear zone anyway, it flows along happily unless you can make it even easier to create frictional sliding. So there's this ongoing competition between fracture and flow. Now let's look at a totally different end member, which is something that is dry. So let's take water out of the equation. But my point here was at low stresses, getting to even lower stresses with an increased fluid pressure is one way of triggering localization. But what happens if we change that dynamic and say, well, we now got essentially no water, and we're going to localize deformation into pseudotachelites. So lower crust of Lofoten in Norway, here is a pseudotachelite in dry anorthosite. Here's a zoom in, again pseudotachelite in dry anorthosite, coarse-grained anorthosite, importantly. In the system, we have an example in a place called Newsfjord East, where there are multiple shear zones in preferred orientations. And within those, there is an area of more pseudotachelites. Particularly, there are myelinitized pseudotachelite along the some of the shear zones, but there are also pristine pseudotachelites in areas away from shear zones or between shear zones. In terms of a block diagram, you can picture it like this. You have a network of shear zones, not parallel to each other, but in a few dominant orientations, that together take up overall extensional strain dominantly in this area. And in at least some of those look like this. So here is a myelinite. The dark material here is interpreted as pseudotachelite. So it's pseudotachelites that have then been myelinitized, and the white is anorthosite, but finer grained in these zones. So just to jump straight to how we interpret this, is that you have shear zones that deform by viscous flow. We're at temperatures of 700, 800 degrees. So this sort of depth on the schematic diagram. Diffusion creep in fine-grained anorthosite with a bit of water in it is quite easy. And these shear zones are generally dikes that are a bit finer grained, maybe a bit wet, or they are resulting from previous pseudotachelites that might have increased permeability and got some water into the system, and also has reduced the grain size of the anorthosite. So we have some shear zones that can deform by viscous shear, and internal blocks that can't because they're dry and coarse-grained. So very difficult to deform by diffusion creep, and dislocation creep in anorthosite is difficult at this kind of depth. But the seismic ruptures shown by the presence of pseudotachelite come from what we think the formation of these blocks, because if you're deforming these shear zones that are not parallel, you need to somehow deform these blocks at some point, at least to a small extent. So, dominantly what these shear zones have is a network of viscous flow around stronger blocks. And these stronger blocks locally need to deform at least a little bit by shear. And that's when you get pseudotachelites. So in this case, the localization is not related to a decrease in strength, but rather to an increase in stress. And the stress drops are very different from what we get in wet rocks, which is not surprising. But here we're dealing rather with something that's maybe failure of intact rock, very large stress drops. If we look at displacement against length for these pseudotachelites, we're looking at centimeters to tens of centimeters displacement, fault lengths of meters. If we put that on the same plot as earthquakes, they are much smaller, but they would fit a stress drop line of more like hundreds of megapascals to a gigapascal. We can plot that here. If we calculate the static stress drop, assuming either circular or elliptical ruptures, then we end up in the megapascal to gigapascal scale, but seismic moments of magnitude 0s to magnitude 2s. So they're small, but the total different end member from relational hydroshears in that they are basically complete stress drops in intact, strong dry rock. And to sort of draw an active parallel to that, here is a very long fault in Malawi.
Okay,
Yeah.
sorry. Can I ask you another clarification here?
Yeah.
So if you have this large stress drop and this slip, which sides of slip velocity do you expect in this complex fault zone? Because to have pseudotachylides, you should have extremely large slip velocity, meters per second,
It would need to be meters per second.
but locally. So and
Only
how
locally.
yeah, and how they are associated with the shearing, with the macroscopic slip, that would be completely different in size.
Yeah, but also at a very different time scale, right? So you would have presumably a very steady slip on these shear zones, which then the pseudotachylides are generally dragged into the shear zone. So I would imagine you have, and there's been, I know Luca Menegon's group has modeled this very recently. If you have the shear zones deforming at plate rate or at strain rates of 10 to the minus 12 per second, that kind of thing, you then build up strain elastically in the surrounding, in the blocks between shear zones, basically, because the block is deforming. But it can't deform by viscous creep, so it deforms elastically until it then locally slips. It has the properties to then deform by seismic sliding, but these pseudotachylides seem to then stop at the shear zones. It's hard to tell exactly because they're then subsequently deformed, but we never see these pseudotachylides cross-cut the shear zones. We've never found one that we can find again on the other side. So they seem to be related to or constrained to the block that deforms. Remember also that we're at 700, 800 degrees already. So you don't need a lot of slip before you potentially hit the melting point.
Yeah, thank you.
So just finally, jumping to a sort of active example of something that might be similar. If you look at faults in Malawi, which is, I think of as a parallel because it's also deforming very old or multiply deformed, old, thick, dry, felsic crust. They have narrow damage zones, narrow dilatant damage zones, less than 100 meters, even though they have hundreds of meters to kilometers of displacement. And the deformation in this part of, so this is East African Rift, is localized seemingly onto very few long faults. So just showing the data on that, fault zone width against displacement. Here is the global data set. The Malawi faults basically fall at the lower edge of how much or of what fault zone width you might have for some given displacement. And if we plot the frequency of faults against their length, there are very few short faults, and most faults are 10 kilometers to 100 kilometers. At least the ones that are mapped. Obviously, there are smaller unmapped faults, but the mapped faults are generally quite long. And if we look at the seismicity, they are seismic throughout the crust. So crust is about 35 to 40 kilometers deep, and earthquakes are present pretty much throughout the crust. In some places, dominantly in the lower crust, at the lower end of this particular border fault. Around this pair of border faults, they are throughout the crust. So there is some way that, in this place, seismicity is localized throughout the crust. If you look at the rocks on the surface, they are typically amphibole to granulite, facies nices. They are foliated, but they are not frictionally weak. The foliation is made up of mostly feldspar quartz, bits of biotite. In places, they have melted in the past, so you have existing melt structures. And if you look at an outcrop at the surface, you have a local fault gouge, very little clays, and you don't have to go far away from the fault until you're back in, well, you go through a fractured, dilatantly fractured damage zone and then into more or less intact rock. But if you think of the metamorphic history of these rocks, and they were dehydrated back in the Cambrian, this is what the compositions would look like if they were dry, which they are. And then basically here is the current geotherm. It is in a stable regime, more or less, independent of depth. There is nothing here that is weak. And you're also a very long way from melting point, which is over here. So, you know, these rocks are strong. They're quite similar to what we have in Lofoten, very difficult to deform. But if you make them wet, same thermal gradient, but you then start doing things like making phyllosilicates, you get much closer to melting conditions, particularly at the base of the crust. So you have this idea that if they're dry, they're going to stay strong. If they get wet, they are metastable. So they're going to do two things. They're going to suck up the water, so it's difficult to maintain fluid pressure, but they're then going to react and potentially melt and potentially create phyllosilicates. So you have a mechanism here of changing fault zone structure by deforming and hydrating it. We have a starting point where this was a hot origin 500 million years ago with steep faults, steep shear zones, relatively weak. The sort of textbook 10-kilometer thick crust, and then viscous lower crust if you have interconnected weak zones, which you probably have in the shear zones that have developed. Then we fast forward to current times. We cool the whole system down. And instead, we now have lower temperatures. We've changed to an extensional regime. We might have a shallow brittle viscous transition if we have interconnected shear zones, so the shear zones might be weak. But if we don't have that, then like in Lofoten, the rocks are going to be frictional. And the only way to weaken the system is to get water into it. So our proposal here is that the seismicity through the crust is driven by the fact that most of this crust is very strong. But if you can start infiltrating water, then it's going to locally weaken. So we have this competition or combination of potentially local high stress points and potentially local weakening by fluids as soon as you've started. But the initial earthquakes will have to be generated by relatively high stresses because there's no fluid source and no source of weakness. So back to these end member fault zones, we have something here that might have looked like this when it was active 500 million years ago in an active viscous shear zone. You've then cooled it down, and it now basically preserves something like this. Everything is quite strong. But then as you hydrate that, you might come back into these sort of regimes over time. So the point I'm making from these higher stress regimes is, the locally stronger rocks make a difference. Even if you're dominantly shearing in a weak matrix, you might deform blocks internally because they need to deform, or maybe more likely, because that's where faults are in subduction melanges, you elevate stresses along the edges of blocks and along existing weak surfaces. You might also have elevated fluid pressure along those surfaces. And that way, you create localization within an otherwise wide, easily deforming, weak aseismic shear zone. Now, that's not a new idea at all. Kenkman and Dresen put this forward back in the late 90s, that if you have a strong inclusion, then you see finer grains, recrystallized grains around it, which implies that you have greater stresses. And they made some calculations in that you have stresses potentially more than double the average generated around rigid inclusions. And that would be where you would most easily start new slip. And we played with this. Adam Beal did a lot of work on this idea of how you distribute strain rates and stresses in deforming zones. He set up something like this. So here is a finite element numerical code. Purple is slow strain rate, yellow is faster. And as he shared this, which had these clasts are 1,000 times stronger than the matrix, the elevated strain rates happen basically between the clasts, and the more clasts you have, obviously there's less material to deform, of the weak material to deform, so strain rates are higher. But that sets up, my final point here on a stress-dependent heterogeneity in these heterogeneous, mechanically heterogeneous shear zones, in that if you have, in these three examples, same geometry, but if you have a driving stress that's near the yield stress of the clast, then basically everything fails. Doesn't have to be as high as the yield stress, because so I was just trying to say the stresses are elevated around strong inclusions. So you approach that, everything fails, strain rate is homogeneous. Reduce the stress on the basis that the matrix can deform quite happily at much lower stresses than the clasts. Then you still have the occasional bits of failing clasts, because stresses are elevated locally, and you get sort of a bimodal distribution of some clasts that are not really deforming and some that are keeping up with the matrix. This would be somewhere where you have an aseismic flow with accompanying failure of clasts, and then you reduce stress more relative to yield strength. So you could obviously do the same thing by reducing yield strength and keeping stress the same, so elevating fluid pressure, for example. But you need to be quite far from the yield strength before clasts stop failing. Even at 34%, at less than half the yield strength, or applied stress less than half the yield strength, you're still seeing quite a few clasts failing as a consequence of aseismic flow. So the point of that in a diagram form is, if you have shear stress, applied stress over yield strength against strength contrast, as we get closer to the yield strength, everything fails, either because you elevate the stress by aseismic flow, or you locally decrease the yield strength by, say, increasing fluid pressure. And that's easier and easier to do the greater the strength gradient. So if the strength gradient is 1, then it's all just going to deform in one way. But if you increase the strength contrast, then at smaller and smaller stress relative to yield strength, the more sort of rich behavior you can get. So I've gone a bit over my time, so I'm going to stop there and just leave those conclusions up.
Okay, but we just lost your conclusion. But okay, but fabulous talk, and I think the timing is perfect. Okay, so would you like to put part of that slide back?
Or put that slide back for a second. Okay.
Yeah. Well, I don't know. You could be in some, like this kind of mode is perfect. Okay, listen, let me invite people to unmute long enough to join me in thanking Ake for a fabulous talk. Really great, really fun. And okay, clearly along the way, there were people already asking questions, so we can open it up. Invite people to use that raise hand feature. It's the easiest way to operate, but especially invite early career people to join the discussion. There's usually plenty of time, so please raise your hand, join the discussion. Bin Hao Wang, please go ahead.
Thank you, Aki, for the great talk. I'm wondering, as a seismologist, if we understand these small scale finite thickness processes that happen within the finite thickness, where you have brittle and ductile deformation in a glass matrix setup, what would be the implications for what you see on a seismogram, or kind of slightly bigger land scale? What would be the implication? Thank you.
That's a really good question for maybe more for seismologists than me, but I think what we'd love to know from seismology is what if we can really constrain these processes that we definitely see in the rocks. We know there are broad zones of finite strain with embedded slip surfaces that we would interpret as potentially failing seismically. So if what would an earthquake like that look like in a seismogram compared to one that's in a, say, fractured medium? And I don't necessarily know the answer to that. I'd love to know an answer to that, and how much. I think there has been some work recently on imaging that there are multiple slip surfaces like this present in at least megathrust faults. Seen, for example, from that you have a distribution of well-located earthquakes within a wider zone. So I guess that's one thing. Would be the distribution of small events, what they would look like if you could locate them well enough. It would also potentially, there might be things one could say about the seismogram depending on what the medium is, whether it's a ductilely deformed medium or a more rigid medium, but that's maybe on the time scale of an earthquake. I'm not sure how well you would see that. So yeah, it's something we could speculate on at length, and I'm not sure if I'm being useful.
No, thank you. Thank you for your insights.
Okay, really, this fabulous talk. Really, so many interesting things in it. I do have a quick question before I turn it over to Massimo, and I'm going to encourage other people to join the discussion. But when you were talking about the anorthosites, you talked about these blocks that were breaking between them, say between shear zones. Can I call those factoids? Or are they too big?
Yeah, I guess you could. I mean, I think factoid's often used for something, I guess, rigid in a broader shear zone. Whereas here, I think the thing about the anorthosite in Lofoten is the proportion of shear zones is tiny compared to the proportion of blocks. You have an anastomosing system of relatively thin shear zones in a very big area of anorthosite. I guess they're still sort of factoids in the sense that they're defined by being surrounded by shear zones.